Alexei, you ready?
Yes, yes.
Okay, so then welcome everyone to the, I actually lost the count of number of seminars we already had, to the nth session of the Wednesday nights of Petri nets and their extensions series. And tonight, you can see a lot of light, so I could even say today still, we're having Alexei presenting his work that will essentially tell us what happens when we discover some models and those models do not fit the reality, and what are the ways actually to fix the situations without rerunning our discovery approaches, discovery algorithms on our logs, and instead just try to apply something that is a little bit more clever and that deals with these problems of non-conformity in a modular way. So as you can understand, this is yet another presentation on from the process mining domain, which I think is going to be very interesting for all of us. So Alexei, please, the virtual floor is yours.
Thank you for this introduction, Andy. Hello, and I will try to explain this subject. First of all, I would like to thank all co-authors of this work and colleagues from Spacelab, which participated in obtaining these results. And I would like to thank student assistants and many contributors to PROM framework, because these results will be completely impossible without many PROM plugins which are implemented by community. So I will start from the beginning, and I will try to be in time and to be not how to say very to be concise, and I will start from the beginning. Many modeling notations are considered in within the domain of process mining. Here you can see heuristic nets, fuzzy models, and the visual notation from inductive visual miner, and of course in the center of it there are Petri nets. So in today's talk we consider so our process models are Petri nets, and here you can see this very well-known picture, which is in the beginning of many process mining presentations, and I usually call it process mining and its environment. So we have real world, and we have these two rectangles below, which show event logs and process models and types of algorithms which allow us to move from event logs to process models, to check conformance between these two type of artifacts, and to enhance process models. What is important here is that these event logs are not just some how to say artificial data, but they are obtained from real life systems by logging processes, and that is why they allow using these event logs. We can not just consider models as results of expert work and as an essence of expert knowledge, but we can really check if these models conform the reality. And so to do so, there are different approaches, but from my point of view, the most improved and as I can see from framework usage and actually other libraries usage, the most widespread approach is alignment-based conformance checking. So this approach is based on making such alignments like the ones shown in this slide, and these alignments consist of actually pairs of log and model moves of moves in logs and in models, and these pairs can be so consistent or inconsistent. Like here we can see that this log trace is cannot be directly replayed by the model, and in such cases alignments contain skips for moves in the model or for moves in the event log, in the trace of an event log. So here we can see that there are two skips. We can of course count these skips for all traces in the log, and then somehow calculate numerical metric which will show the degree to what a particular model conforms to a particular event log. And there are several metrics for which are considered in process mining as important metrics for process models. First of all, it is fitness, also called recall. I think this more later name can help researchers from different fields, such as machine learning or data analysis, to understand what fitness metric is. So fitness of a model shows that this particular model can replay all the traces from a given event log. Precision shows us if this model add many more additional behavior to the behavior which actually needed to replay the event log. For example, in this picture, we can see the model in the below left corner, and this model is actually fitting one. So this model is able to replay all traces from this event log, but this model is very imprecise. So it allows many more additional behavior. For example, we can have many how to say many repeatings of different transitions, which will lead to very long but unnatural traces. At the same time, we can have a very precise models, like the one shown in the bottom right corner, which are just such a model is just a rewriting of the event log. So we have for each trace from the event log, we have a branch in this model of a branch of transitions in this model. So this model is in some sense too precise, and it will have very low generalization, because this model had no sense to the event log. The last metric which I did not mention is simplicity, and actually it can be said a lot about simplicity of models, but simply speaking, the model is simple. So if we have two models, and so if these two models have the same behavior, then the model with the lower number of elements and the easier structure will be considered simple. But of course, there are different metrics, and so different concrete metrics for simplicity. And of course, simple models usually are better for human experts, and for automated processing as well. So when we say about conformance, we talk about all these metrics. Even simplicity can be considered as a part of a conformance metric, of a conformance of model conformance to the in this talk we focus mainly on fitness and precision, and we'll leave simplicity and generalization mostly out of scope. And the repair methods can be placed in this enhancement part of this, how to say, process mining world. Yes, but inside our repair methods, we will use algorithms from other two subfields. And what is important to say here is that in our method, we consider models as a subject of errors and some inconsistencies, and we consider event logs as a normative, so good behavior. So it is, of course, it is important to look at the problem, to approach this problem differently, and to consider event logs as erroneous artifacts. But for us, event logs are correct, and models can be incorrect. So we want to repair process models. Why do we need repair when we have actually discovery algorithms? For example, I will try to motivate the need for repair methods with this rather simple example. We have this relatively large Petri net, and what we do, we just swap two transitions in this net. You may note that these transitions actually are relatively close neighbors in the structure of this model. So if we check fitness using basic prompt framework algorithm after swapping these two transitions, we will have, if we swap these transitions and we will use the same event log as before, we will have something like so almost fitting event log to the model and event log almost fit together, almost perfectly fit together. And now we want to somehow obtain perfectly fitting model. So we want to obtain a model which will be able to replay all traces from the event log. What if we just apply discovery algorithm to the log and try to reconstruct the model? Then we obtain something like this, like that model. It seems that it is not very so structurally similar to the initial model. In some cases, then what we're interested in is only behavior. Everything is fine because behavior of this complex model can be even the same with the initial model. Actually, here this is not the case, but it can be. If we are interested only in behavior, everything can be fine. But yeah, and another example using inductive miner. So they have very different model as well. But if the initial model is used by a human expert, and maybe this model has been made by a human expert, then it is possible that we need not just to obtain the same behavior, but we also want to preserve useful properties of this model, such as human readability, and we want to preserve the structure of this model. Yes, because if we ask if we ask a human to repair such a model, he or she will just swap these two transitions backwards and will easily repair such an example, and will preserve the most part of model structure. So how can we achieve such a result? How can we repair such models without complete rediscovery? And that is a question to that I will try to answer in this talk. So this is a general scheme of process model repair. Here we have a process model and an event log, and we try to somehow modify process model in such a way that the new repaired model will conform to the event log. Actually, there are many works in this field with different problem statements and different solutions, and so I will consider firstly our solution to this problem, and then to consider a couple of other solutions with which are suitable for similar problem statements. And I will not consider works with in this talk. I will not consider works with which are intended to solve different repair problems. So, as I said previously, we have Petri nets as process models, and actually these are labeled workflow nets. And we have event logs. And in this work, event logs are finite multisets of traces. So yes, and our problem is how to automatically construct a Petri net such that new repaired Petri net will be able to replay all traces from the event log. So the new model will be perfectly fitting, and it will be as precise as we can do it. And these models, and we want these models will be structurally similar. In our approach, we assume that all transitions of the initial model have unique labels. All non-silent transitions. So all transitions with labels have unique labels, and we assume that that the event log contain no activities which are not present in the model. So the event log contains no additional new activities. This is important because actually an event log may contain these activities, but they will be ignored. So if you want to add new behavior, add new activities to your model, then in the end of my talk, I will refer to another process model repair methods which are good at it. So what we propose? Our idea is very simple, and came from, how to say, the textile industry. Then you have a pair of trousers, and you have a hole in your trousers. You just make a patch to repair them. And in this work, we try to do the same with process models. The idea of our modular scheme is as follows. First, to decompose a process model using one of decomposition methods. Then to decompose an event log using projection procedure to obtain a set of sub logs related to subnets to model fragments. Then to check conformance for each pair of a sublog and a subnet, a sublog and a subnet, and then by doing so we can split this subnets, this set of subnets into two sets. In the first one we have non-conforming subnets, and in the second one we have conforming subnets. For all subnets from so all non-conforming subnets can be simply rediscovered using discovery algorithm, which will guarantee perfect fitness. And then we can compose the final model again from these fragments and to obtain corrected workflow net. So the idea is simple: just to decompose model and to replace non-conforming or unfitting subnets with fitting subnets. And in our work, we formulated this scheme and proved that that actually it guarantees or ensures perfect fitness of the final model with several constraints. The first constraint is that our decomposition function have to be a valid decomposition. I will not consider this in detail. This notion of valid decomposition was proposed by Wille van der Aalst in his works on decomposed conformance checking. And simply speaking, decomposition is valid when the initial model, then all transitions in the initial model have unique labels, and then we split this initial model on subnets only by splitting, only by how to say, cutting using these transitions with unique labels. So in the reminder, I will show you an example, and you will see that so it is intuitively obvious that what it is. So for repair, for repairing of these subnets, we have to apply so-called perfect discovery functions, So these are discovery algorithms which can guarantee perfect fitness of the discovered model. For example, inductive miner with a particular settings, all these return perfectly fitting models. The same can be, the same guarantee is satisfied by an ILP miner. And that's why we use these algorithms. But actually any algorithm, any perfect discovery function can be used there. And to compose the final model, we use just a simple transition fusion function. So we just use transitions with the same labels. So then we decompose function. Then we decompose the initial model. We obtain so in this several so each transition with unique label is splitted between different fragments, and then we just fuse all these transitions with the same name, and so without, how to say, without any glue, compose the final model. In particular, for our experiments, we use alignment-based fitness checking to compute fitness. We use inductive miner or ILP miner to discover these subnets, and we use maximal decomposition algorithm to decompose the model, and simple fusion of transitions to compose the model. So let me consider an example of how this algorithm repairs a model. Here we have a very simple Petri net and the very simple event log with just two traces, and in which in this event log, if we check conformance for this event log, we will see that only two events in this in the second trace have to be swapped to or two transitions in the model have to be swapped to repair this this model. So first we use maximal decomposition to decompose the model. To maximally decompose the model, we have to cut all transitions with unique labels between the fragments. So if we have so if we can cut a transition, then we do so. So here we obtain 6 fragments, and our model is decomposed in the 6 fragments. Then, using simple projection, we obtain 6 sublogs which correspond to these submodels. In each of the sublog, only events with the names corresponding to transition labels remain. And then we can check conformance, and we can see that the only one fragment have inconsistencies here. Then this fragment is rediscovered. For example, here we use inductive liner, and then we fuse transitions with the same labels. At the end, we obtain such a model, and this model perfectly fits the event log. This model, if we want, can be transformed to a workflow net if it is needed. So the problem here is that we changed model behavior significantly. Of course, we can replay these traces for which we want to they to be replayed by this model, but we actually reduced the number of additional behaviors which were able in the initial model. So how to solve this problem? Actually, 3 solutions can be proposed. The first solution is just to remove these additional constraints. Yes, additional constraining places, the artificial initial place and the artificial final place. So this will not affect fitness of this modified model, but this modified model will be less precise, as these tau transitions at any moment are able to add tokens or remove tokens out of our process, our model. So our solution is to add traces with the needed behavior to the event log which used for repair. This is actually not so easy because this second solution need manual work by experts. So when we make these projections, a human expert have to investigate what behaviors can be deprecated by this artificial places, and have to add such behavior to the event log. So this solution is not suitable, and then we actually decided that the problem, the reason of this problem is that during the repair of this fragment, which we cut it from the initial model, we actually changed the border transitions of this. So they changed the rules for border transitions of a fragment. And then the third solution is possible, is just to wrap subnets with inconsistencies before the repair, to be sure that these border transitions will be untouched during the repair. So as when we repair trousers, it is not very convenient to apply patch with the size of with the exact size of a hole. Usually patches are a little bit larger, yes, than the size of a hole for that a particular patch is applied. So the idea is here is similar, and then we add additional step here, step of fragment enlargement, and the example is as follows: the same model, slightly different event log, and the same projection procedure, but then as in previous case, we have the only one unfitting fragment, but here we can what we do here, we actually add all neighbor fragments to this one. When we add these fragments, we can be sure that the new border transitions will be unaffected by our repair. And indeed, we use inductive miner, and then we obtain model of such type. In this model, so this model perfectly fits the event log, and now it have no problems such as in previous case. Yeah, but still, even this improved method have some imperfections. So it is well suitable for all cases. Then our then the problem is localized inside one of the decomposition fragments. So when, for example, we swap transitions in one fragment, but what if transitions are swapped between? So if we swap transitions between if we move some transition in a far standing part of a model, then when we apply our maximal decomposition, the problem and so the roots of the problem will be not in the same fragment as where solution for this problem can be applied, and then such such cases we call non-local inconsistencies. Repairing such cases using our improved algorithm actually can lead to spaghetti-style process models. That is not what we want. And the solution here is just to find all unfitting fragments and to glue them to find a model fragment which will cover all these unfitting submodels. So we add additional evaluation block here with so we introduce a loop in our repair algorithm. An example of solution can be shown here. So we have two unfitting fragments, and so we in the initial model we just swapped two transitions in fast-ending fragments. Then our algorithm begin from or start from one of these four fragments, and then at each step it just add all neighbors to the current fragment, and it adds so the algorithm adds more and more neighbors until it covers all unfitting fragments. Of course, you can see that here we have so here we also covered unnecessary part of the model, and I will return to that. So using this greedy repair, as we called it, we obtain such results. So in the initial model, we swapped two transitions, and then actually a large part of a model is reconstructed using this greedy repair. So in the worst case, the greedy algorithm rediscovers the whole model. So in the worst case, we just rediscover the whole model. If a human expert at the beginning of this process knows that this so that problems are completely non-local then it will be better just to apply rediscovery. But if but it can be unknown, and then if the model is large, there are cases then this greedy repair can be useful. We evaluated all these algorithms using such a scheme and using our event log generator to generate logs suitable for repair. And so for local repairs, we obtain rather nice results in comparison to complete rediscovery. So here, only these fragments touched by our repair algorithm. The same is for slightly larger models. And okay, I will skip tables, because so here we can see that the precision of so using the improved algorithm is more or less okay according to the initial model. We also conducted experiments with larger process models, and yeah, so actually the larger the model, the more useful our approach is. For very large Petri nets, the greedy technique can be even the only possible way to repair such model, because rediscovery can be so, because for such huge models, process discovery, actually event logs, which are used to construct initial models, are large as well, and contain a lot of different event classes, and discovery algorithms cannot rediscover a model for the whole event log, but using the greedy technique, we use just a projection, just a sublog, and for such a fragment, it is possible to reconstruct this model. We also improved our greedy algorithm for just to so this improved version just selects only needed submodel to cover all unfitting fragments, and this made by constructing special covering tree. So we make a structure which we call decomposition graph. In this structure, nodes are related to decomposition fragments, and edges connect these nodes. And these nodes can be red or green. So red nodes are related to unfitting fragments. And then we just need to construct a tree covering all these red nodes. And of course, it will be nice to build a minimal tree, but this problem is hard to solve. So our algorithm actually does not guarantee construction of a minimal tree, but it is some approximation for such a minimal tree, but it is better than so it is our results show that our in most how to say real life examples, we actually obtain tree of minimal size, but there are examples then so it is possible to find an example which will how to say break our algorithm. And here is an example of our approach. So actually, for such a small models, it usually reconstructs the initial model usually finds a way to reconstruct the initial model. Our project, so all the results of our project are published, and at this page, at the site of our laboratory, you can find all these, so links to the repositories, data from these projects, and links to the papers. I also want to mention a couple of other important approaches which are very nicely how to say, these approaches and other approach can be combined in a more complex repair scheme, which will cover all, maybe not all, but most possible repair cases. So in our approach, we add no behavior to the model, but we can rearrange transitions in such a way to replay existing behavior from the event log. In this approach by Dirk Falland and Wil van der Elst, authors consider the problem of how to add behavior, of how to better add the model from the event log. So we have a process model and we have an event log which contain additional new behavior, and we want to somehow change the model, preserving its structure, but to add new behavior. So here I show a basic example, and what is the idea of the repair of this approach? The idea is to add transitions to suitable places. So here we have D, and here we have also D skipped. So we can add D to place C1, as we can see here in the event log. So the D will be executed between A and B. And we can add tau just to skip D here. So this new model will be able to replay this event log. It is possible, then there are a lot of, so even for a single trace, we have a lot of transitions. So we need to add a lot of transitions to repair model just to replay a single trace from the event log. So then it is possible actually to find subtraces, to construct sublogs, and to build subprocesses using process discovery. So authors consider this problem. They introduce the notion of locality of these additions, and they define subtraces, which consist of how to say, of events with model skips related to the same locality. And then their method is able to add subprocesses. It is also possible actually to add cycles, and in this picture the authors show how all this look in real life. So these subprocesses can be relatively large. And this method, so this repair method has been improved by another group of researchers, and what they considered, they considered such a basic repair operations like adding a transition with a needed label or adding a tau transition. And they considered repair as an optimization problem. So they introduced so-called repair recommendations, and these repair recommendations are actually consist of a large number of such basic repair operations when we add a transition with a particular label. And then it is possible to find optimal additions, yes, using different optimization methods. So why do I consider these repair methods? First of all, because this paper on repairing process models is one of the first papers in process mining field on this subject. And secondly, because these methods to add new behavior to the model can be successfully used together with our repair approach when we add no new behavior but rearrange existing behavior, and actually our method will remove from will be able to remove from the process model behavior. So how to say, which will be unneeded. So finally, I would conclude by discussing open problems in the field of process model repair. Actually, there are a lot of them, but I would stress the last one in this list because I think it is because this open problem is related to to the whole event of Wednesday nights of Petri nets and their extensions. As I know, there are no repair methods for Petri nets with extensions. I only know that there are methods that there is a paper on repairing time. I'm not sure time or timed Petri nets according to timed event logs, and but in this paper they actually repair time constraints. They repair no net structure. They just find suitable timings for Petri net to be able to replay the event log. But for example, Petri nets with data or object-centric Petri nets, or nested or reference nets, for now there are no approaches to repair to automatically repair such models based on data from some real life information system. So that's all what I wanted to present today, and have a nice healthy spring, everyone. Yeah. Question, I would be happy to answer.
All right, Alexei, thanks a lot for this extremely interesting presentation, actually, with so many different approaches and ideas regarding the quite, I think, a challenging problem of repairs. So as usual, probably let's wait whether there's someone in the chat having questions. Okay, there was no one so far. So maybe let me start asking a very trivial question. That is, have you? So you obviously mentioned it as a future work, right? The repairs for models with different extensions. Have you thought specifically about some concrete class of Petri nets for which repairs, or let's say for which the techniques that you probably already know would be easy to transfer, or this problem is, let's say, too challenging and would require a lot of deep research?
That's a good question, actually. I think it depends on how to say on type of an extension, because for example, if we have a typical an ordinary Petri net structure, but with just an addition, for example, nodes with special semantics, like, I don't know, like in Petri nets with data, if we consider some of Petri net transitions as or like in DB nets, yeah, then we consider some nodes of a net as readers or reading or writing nodes. Then it seems for me that it will be possible to apply just these methods for ordinary Petri nets, but together with additional constraints, just to to be sure that how to say that the problems or inconsistencies are not related in a particular trace to inconsistencies, to, I don't know, data inconsistencies, for example. So then it will be possible to apply these basic repair techniques. Actually, for I don't know, nets within, for extensions from the field of nets within nets, it is not that easy from my point of view, and I think that specific methods have to be discovered or proposed. I would stress that the most important thing here is that all these repair methods are based on conformance checking methods. You can see that our modular this how to say this idea of patching is based on decomposed conformance checking. The repair which add subprocesses is also based on alignment-based conformance checking. So it seems for me that all repair methods, or most of repair methods which I know, are actually how to say conformance metric related. Then to propose good automated repair methods for Petri nets with extensions, we actually firstly have to propose good conformance checking methods for these particular extensions. And for example, for as I know, for these nets, so for these extensions, for nets within nets, for now, they're only very, how to say, simple, or so only first steps are made to propose conformance checking methods. So when we will have conformance checking for such models, then it will be possible to repair them effectively.
Right. Essentially, your message is that before you even start thinking on doing any kind of repairs, please make sure that you're feeling quite okay on the conformance checking side, right?
Exactly.
So yeah, I think it's kind of very, it speaks for itself, right? Although there are already conformance checking techniques for models with extensions, for example, like the model that Massimiliano was talking about during one of the last presentations. So the model of DPNs, there are already different conformance checking techniques developed for it, and I think the last one was precisely based on the alignment. So I think, for example, one could already start thinking on how to apply the techniques, the repair techniques on those models, or even how to transfer them there. But again, the question probably remains is, how would you do this modularly, as you were suggesting here? So whether the data that you're dealing with, so that although in this model of DPNs, the data component is not as sophisticated as, for example, in some other models. Still, I don't know. I'm not sure whether it will actually create any problems for you.
For now, I would say that I cannot say it for sure. Yeah, but it seems that if we can somehow localize an extension, so not an extension, but for example, if we speak about if we talk about reading or writing data, or I don't know, checking cards depending on information in database. If this if our model, if you can decompose our model such in such a way that all reading and writing all to a particular data variable or data object, then it seems that it will be possible to replace the whole such fragment. So if our extending element can be somehow localized and somehow placed in such a submodel, then it seems that it can be possible to apply the same idea. I would not say the same method, but the same idea. So the general thing here is to be able to somehow cover one of model, I don't know, aspects with such a submodel, and then it can be replaced, and the remaining model part will stay untouched. Yes.
All right.
If I answered, how to say, in an understandable way.
No, well, that's for sure. I think there is actually, it's probably a very hot topic. So I will be curious to see how many people will pick it up in the next years and provide results in it. So thanks a lot for your answer here. Other questions?
Yeah, I have one, but I had to quickly search for the right button. Thanks for the talk. What I always find difficult with all the repair methods is how do you choose the different options? So how do you know which of the different techniques is better? Or what is better in this case? Is fitness and model structure the right way to say, well, this is how we improve or repair?
That's a very good question honestly, I have no good answer to this question because actually, so this greedy algorithm which I presented actually is one of is a result of trying to answer this question, because the introduction of this algorithm is our attempt to given some automated methods which will how to say which will allow to start just to use it, and then to and then this method will or will select some part of a model and some small part of a model, and the user of this algorithm will obtain the repaired model with more or less the same structure, or the algorithm will, if how to say, the situation is very bad and the inconsistencies are non-local, then the algorithm will just rediscover the whole model. But this is our attempt to answer only for fitness, and only for so yeah, only for fitness. And then still so there is a question if we really in all cases need perfect fitness, or how to say, slightly unfitting model with better, or slightly unfitting but more precise model is better. And as I know, for now, there is no good answer, but there is a huge, how to say, so this is one of the very important topics in within process mining, and actually there are even there were even meetings on how to define different precision metrics and how to define different simplicity metrics, and what and how to actually describe model qualities. And from my point of view, for now, it is so. The question is still open in general. We looking at it from, I don't know, technical side. We're thinking how to propose an algorithm to obtain good results for a particular numerical metrics. And it is always a good question, and it is still a good question, if this if a particular value as a numerical metric for fitness or precision is enough to say that it is a good model. I would answer that it is not enough, but I cannot answer how to actually how to construct an algorithm to make a model suitable, yeah, for all cases. It seems that it depends on a particular case, and now it is still a job for an expert, as for a user.
Yeah, no, I also still don't have a proper answer to this question. So it's one of the things we still need to solve in process mining.
Exactly, yeah, I agree. And actually, it's the very popular in the very popular field of machine learning now. They have, as I know, the same problems.
Yeah.
Well, you'll probably address it pretty much empirically, right? So you just pick up a metric and then you try.
Exactly.
I think probably again, following the proposal on metrics that Artem gave during his presentation on this various new metrics for was conformance checking, right? I think just like picking up all of them and just for the whole list, running all possible experiments and just at least seeing what's good about it. That will be extremely interesting.
Yeah, definitely.
Yeah, I agree.
Other questions? Okay, so then I would say let's call it a day. Let's thank again our speaker. Thanks a lot, Alexei. The round of virtual applause.
Thank you.
And right, so we hope to see you during at our next meeting, at our next seminar that will happen in a week. So we still need to agree on the time, but it will be probably happening in the morning, as we will be again hosting another speaker from the down below from Australia. So please be prepared. Thanks a lot, and see you in a week.
Yep. See you next time.
Bye.
Bye.
Bye bye.
Goodbye.